Good morning. Today let us attempt a tutorial on draft tube theory. We will solve a few numerical problems based on draft tube theory. For the first problem, a conical draft tube having inlet and outlet diameters 1 meter and 1.5 meter discharges water at outlet with a velocity of 2.5 meter per second. Total length of the draft tube is 6 meter and 1.2 meter of the length of the draft tube is immersed in water. If the atmospheric pressure head is 10.3 meter of water and the loss of head due to friction in the draft tube is equal to 0.2 times velocity of head at outlet of the draft tube. Find pressure head at inlet and efficiency of the draft tube. So the schematic diagram of the draft tube is given. Here in this diagram we have marked the inlet section as 2 2. You can see here the inlet section of the draft tube is marked as 2 2 2. Section 2 represents the inlet section and the section 3 represents the exit of the draft tube or outlet of the draft tube. Then here we have given the inlet diameter of D2 of the draft tube 1 meter, exit diameter D3 as 1.5 meter. Then the exit velocity discharges water at outlet with a velocity of 2.5. That is V3. We have given V3 as 2.5 meter per second. The total length of the draft tube is given. That is, total length means this length. So this length is 6 meter. Total length of the draft tube is 6 meter. And the depth of immersion that is represented here as y. This y is 1.2 meter. That means 1.2 meter of the draft tube is submerged in water. So the suction head of that draft tube, that is HS, which is we call as suction head of the draft tube. So HS will be this 6 minus 1.2, so it will be 4.8 meter. Then we have also given the atmospheric pressure head is given. Atmospheric pressure head is PA by specific weight W, so that is 10.3 meter. Then head loss due to friction, that is HF. Head loss due to friction, HF is 0.2 times velocity of head at outlet. Outlet is V3 square by 2. So this is velocity head. V3 square by 2 is the velocity head at the outlet of the draft tube. That into 0.2 is the head loss in the draft tube due to friction. So these are the non-data and relation in the question. Now we have to find what first thing is pressure head, that is V2 by W. So this is the pressure head of the draft tube inlet. So this diameter, then second draft tube efficiency. So these two parameters are to be determined here. So now let us first attempt to calculate the discharge of the draft tube. Let us say Q, which will be A2 multiplied by V2, or is also equal to A3 Vk. So here we have given exit velocity of the draft tube and the exit diameter. So from that you can calculate the discharge. So the discharge Q equal to A3 is pi by 4 D3 square into V3. So this is pi by 4 into 1.5 square into 2.5. V3 is 2.5 meter per second. So the discharge we get as, if you calculate, after calculation you get this value as 4.4178 meter cube per second. So this is the discharge. So with this discharge value you can find the velocity of the inlet of the draft tube. The velocity at draft tube inlet. So V2 will be discharge by V3. So discharge value you can substitute here, V2 equal to discharge is 4.4178 is divided by area is 5/4 into 1 square. D2 is 1 meter. So that gives the inlet velocity as 0.625 meter per second. So this is the draft inlet velocity. Now to determine the pressure head value, let us write the draft tube equation. So from draft tube theory, so from draft tube theory, you can write the pressure head P2 by W, pressure head of the draft tube inlet equal to, we have derived this equation, so you may refer to that derivation. So PA by W is the atmospheric pressure head minus Z minus HS minus V2 square minus V3 square by 2G minus HF. This equation we have derived to show that the pressure head of the draft tube inlet is below atmospheric or vacuum. So this is the situation we have, and in the question we have given that atmospheric pressure head is 10.3 meter. Atmospheric pressure head value is specified here. So let us substitute. So we can write P2 by W equal to PA by W. So this is 10.3 minus HS. We got HS as 4.8 minus V2 and V3. We have this V2 and V3 as V2, it is 5.25 square minus 4.4, 4.4 is 2.5, 2.5, 2.5 square by 2 into 9.81 is minus HF. HF is given as 0.2 times V2 square by 2g, or V3 square by 2g. So this into 2.5 square by 2 into 9.81. So this HF is HF is V2 square by V3 square by 2g into 0.2 times. So this is what the HF. So from this equation you can resolve this equation, calculate this value of P2 by W, and you will get it as 4.27 meter. So this is 4.27 meter, and this is your in absolute unit. So 4.27 meter absolute, that is the instructed at draft tube inlet. Or you can also write this in terms of 10.3 minus, if you take 4.7 meter, so this will be 6.03. So this is the backbone. So you can, so the pressure head either it is 4.27 meter absolute or 6.03 meter backbone. So that is the pressure head value. Now the draft tube efficiency, you can directly write down that draft tube efficiency equation. Efficiency is eta d equal to, we have this draft tube efficiency as V2 square minus V3 square by 2g minus HF divided by V2 square by 2g. So this is the draft tube efficiency relation, and again here you can substitute for this HF as eta d equal to V2 square minus V3 square by 2g minus, this is 0.2 times V3 square by 2g. So this is divided by this V2 square by. So you can substitute the known values, so V3, V2. So this is, you can write, further simplify this V2 square minus V3 square plus 0.2 times V3 square by V2 square. You cancel that 2g from numerator and denominator, you can cancel out 2g. So now to substitute the, so what you can obtain is, so we have that values, substitute the values of V2, what we have is 0.625 square minus 2.5 and 2 times 2.5 square divided by 2, which is 5.625 square. So there is substitute and get the efficiency as the calculate, you get the 0.763. It is the efficiency of the that completes our problem number 1. Let us attempt another problem on draft view. A Kaplan turbine develops 4 megawatt of power under a net head of 6 meter. A vacuum gauge connected to the entrance of the draft tube indicates a reading of 5 meter suction pressure head. The elbow type draft tube of the turbine has an inlet diameter of 3.2 meter and an outlet area of 25 meter square. The draft tube efficiency is known to be 75% and the draft head is 2 meter. Calculate the overall efficiency of the turbine, the head closed in the draft tube and power thrown into the cages. The diagram is also given. So we have a elbow type draft tube connected to a Kaplan turbine. So here the draft tube inlet is marked as 22, section 22 represent the draft tube inlet and 33 represent the draft tube exit. Then the suction head, that is height of the turbine inlet above the tail race, that is suction head is HS, and this is the tail race level. Then first of all let us write the data which are specified in the problem. So given, so we have given shaft power of the turbine is 4 megawatt. Then head 6 meter. Then pressure at the turbine inlet, pressure head at the turbine inlet is given, that is P2. Pressure head is given as P2 by W. P2 by W equal to 5 meter, that is 5 meter, and it is a vacuum pressure. It's negative pressure. So given that the vacuum gauge connected records 5 meter suction. That means V2 by W is 5 meter vacuum. Then the exit inlet, sorry, the inlet diameter V2 0.2 meter. Exit area is given. A3 is 25 meter square. Then draft tube efficiency is 75%. Then draft head to be drafted is this suction head HS. HS is draft head means the height of the turbine inlet above the tail race. That is 2 meter. So we have listed the data which are specified. Now we are asked to find first one, the power developed. Not overall efficiency, sorry, overall efficiency of the turbines and power. Eta not overall efficiency of the turbine. Then friction head lost in the draft tube. And the third, power wasted. Power thrown into the table, power wasted in this. So these three quantities we have to calculate. So let us begin from the given dimensions of the draft tube. The inlet area of the draft tube you can calculate from the known diameter. So it is pi by 4 d2 square, which is pi by 4. d2 is 3.2. So 3.2 square. So to calculate it, you will get this as 8.04 meter square. Then exit area is directly given. So A3 is 25 meter square. So it's given. So you have inlet exit area now known. So you can find the relation between fluid velocity at draft tube inlet and draft tube outlet. So for that you can use the continuity equation. This we have A2 V2 as equal to A3 V3. So this you can write like this: V3 by V2 equal to A2 by A3. This A2 is 8.04 divided by A3 is 25, and this is 0.321. So the relation between velocity of fluid at draft tube inlet and draft tube exit is V3 equal to 0.321 V2. So this is one important relation that we need to mark as 1. Now let us consider the equation for, or let us write the equation for the pressure head and draft tube inlet. So from draft tube theory, we have pressure head at draft tube inlet. We have derived this equation in our earlier classes. So the draft tube inlet, at the draft tube inlet we have the pressure head as E2 by W is the pressure head. This is equal to PA by W is atmospheric pressure head minus suction pressure head or suction draft head of the suction draft head HS minus and V2 square minus V3 square by OG minus friction head HF. So this equation we have derived. You may refer the earlier class note. So now let us substitute the given value of the pressure head at draft tube inlet. We have given E2 by W as equal to 5 meter, which is vacuum. Negative pressure it is. So vacuum, that you can convert into absolute pressure as this is also equal to what we know is, we know atmospheric pressure head PA by W is 10.3 meter of water. So atmospheric pressure head is, so this is atmospheric head. So this value you may note down for doing in the problems related and that involve this atmospheric pressure head. So now let us substitute the value of V2 by W So this is, since it is given in vacuum, we can convert V2 by W is also equal to 10.3 minus 5. So this is equal to 5.3. So this is absolute value. Absolute. So the pressure head value, either you can say it is 5 meter vacuum or 5.3 meter absolute. Now let us substitute this value in the pressure head equation. So this 5.3 equal to 10.3 minus. So this equation now. So here V2 by W 5.3. So this is 10.3 minus HS. Minus HS. HS is given as 2. So 2 minus V2 square. V2 square minus V3 square. We have that relation. So I can substitute V3 in terms of V2. This is 0.321 V2 square by 2G minus HF now. Let us now do one thing, that we have given the draft tube efficiency. Let this be let us our equation 2. Our draft tube efficiency is actually, that is given, is 75%. So we can now write the equation for the draft tube efficiency as eta D. The eta D equal to V2 square minus V3 square by 2G minus HF divided by V2 square by 2G. So from this equation, what I can write is, so this I can write as this numerator V2 square minus V3 square by 2G minus HF is equal to eta D into V2 square by 2G. So what I get is now V2 square minus V3 square by 2G minus HF equal to, this eta D is 75%, that is 0.75 V2 square by 2G. So now let this be equation 3. Now see, in equation 2 we have this term involved. Actually, this was not necessary to put this relation. Anyway, we can replace this one. From this, in this equation we can replace C V2 square minus V3 square by 2G minus HF. Instead of this, I can put as eta D into V2 square by 2G. So that I can now substitute in that equation. So our drafted pressure head equation 5.3 equal to 10.3 minus 2 minus, it is 0.75 V2 square by 2G. So this I can write from here as 0.75 V2 square by 2G equal to, this will be 0.35 I minus 3 will be equal to 3, or this will finally give me the value of V2 as 8.86. meter per second. This is the value of the draft fluid velocity and the draft tube inlet. So if you got V2, we can get V3 as it is 0.321 times V2. So it is 0.321 multiplied by 8.86. So this will be equal to 2.84 per second. So we have obtained the draft tube exit and inlet velocity values. Now let us use these values to obtain the overall efficiency and other parameters which are asked to determine. So the discharge through the draft tube we can obtain from Q discharge Q, we can write this as equal to A2 into V2. So that is 8.04, 8 into V2, 8.86. So this we obtain as 71.03 meter per second. So we have discharge value calculated. In the question we have given head and power value. So the overall efficiency of the turbine eta naught, by definition it is shaft power by water power. So shaft power you have given as 4 megawatt. So it is 4 megawatt by W, it is 9810 Q 71.23 into H is 6 meter. So this is in megawatt. So you need to convert that into watt. So efficiency equal to 4 into 10 raised to 6 divided by 9810. So the specific weight, the discharge 71.23 into 10.6. So you get this value as 0.95. That means overall efficiency is 95%. Now the second quantity that is to be determined is friction head loss. Head loss due to friction in the draft tube. But already we have one equation. HF equal to that we can write from earlier equation what we have written here. Equation from equation 3 V2, that equation you can use. So V2 minus V3 square, V2 square minus V3 square by 2G minus HF equal 0.75 V2 square by 2G. So that gives you HF equal to 2 square minus V3 square by 2G minus 0.75 V2 square by Vg. So you can now we take this V2 square minus this V3 square. I can write it as 0.321 V 321 V2 square minus 0.75 V2 square all divided by 2G. So that you can write this as 1 minus 0.75 minus 0.321 square into V2 square by H. So you may now calculate this by substituting the value. So 1 minus 0.75 minus 0.321 square into this is 8.86 square by 2 into 9.81. So after calculating, you get this as 0.588 meter. So the head closed due to friction is 0.588 meter. Now the third quantity that need to be determined is power lost or power wasted to the tail race. That means what we have here is the fluid water after flowing through the draft tube leave it at velocity V3. So the lost energy corresponding to draft tube exit velocity is the power wasted. So this will be equal to W Q into V3 square by 2G. So here this V3 square by 2G square by 2G is the kinetic energy. Kinetic at all, yeah. Kinetic V3 square by 2G is kinetic head of water leaving the draft tube. So that energy is not utilized, so it is wasted. So that you can calculate as 9810 into discharge 71.23 into V3 is 2.84, so it is 2.84 square by 2 into 9.81. So calculating, you get this equal to 28,726 watt, or you can write this as 287.256 kilowatt. So this is power lost due to, so the power lost or power wasted, water power wasted to the tail race. So that completes our problem number 2. Now we will solve one more problem. We'll see one more problem. involved in the cavitation parameter. The third problem you may note down. At a site on a river, the power potential is 225 megawatt under a net head of 15 meter. If desired to operate turbines at a speed of 60 rpm, two choices of turbines as follows are available. Francis turbine having specific speed not exceeding 300. Second, Kaplan turbine having specific speed not exceeding 600. Question is, how many units of each type, all of same size, would be required? The second part, the atmospheric pressure is 9.9 meter absolute and vapor pressure head is 0.3 meter. Calculate the maximum draft head in each case. Critical Thoma number can be taken as 0.36 for Francis turbine and 0.73 for Kaplan turbine. So it's a very simple problem. In the first part, you are asked to determine the number of turbines needed. Two cases, two available types of turbines are Kaplan and Francis. So you have to find out how many of each are required to generate total power of 225 megawatts. So as usual, let us first of all list out the important data that are given. So we have given total power potential or total power that is need to be generated. Total power to be generated is 225 megawatt. So for the given data, given, then available head is 15 meter. Then the rotational speed n, speed of the turbine, each of the turbine is 60 rpm. Then specific speed values of the turbines are given. For Kaplan, specific speed ns equal to maximum value is 300 for Kaplan, sorry, Francis, and equal to 600 for Kaplan. So these two categories of turbines are available, and we have to determine the number of turbines that are needed for generating 225 megawatt. So now let us write the equation for the specific speed. Specific speed, we have this relation n root p by h to the power 5/4. And for Francis turbine, this is 300 equal to n 60 root p is 15 to the power 5/4. So now you can calculate the power developed by one turbine. Therefore, power generated by a single turbine so from the above equation you can calculate it as equal to 21,785 kilowatt. So this is the power generated by a single Francis turbine. So the total number of Francis turbines required can calculate from the total power that is needed to generate this 225 megawatt it is. So I can convert that into 10 raised to 3 kilowatt. 51,785 kilowatt. So that will get us 10.33. So we can say 11 numbers are required. So you need 11 Francis turbine to generate 225 megawatt of power. Now, in the case of Kaplan turbine, specific speed value is 600. So 600 equal to again 60 root P by 15 to the power 5 by 4. So this will give you the P value is the power generated by a single Kaplan turbine 87,143 kilowatt. So this is power generated by a single turbine, single Kaplan turbine. So the number of Kaplan turbines needed. Sure. You can calculate by total power 225 into 10 raised to 3 kilowatt divided by 87,143. So we will get this as equal to 0.58. So we can say the three numbers. So you need 3 Kaplan turbines to generate that much power. So 11 Francis turbines are needed, or if you are choosing Kaplan turbine, you need 3 numbers. So we have quantified the number of turbines required. Now we have to find the maximum suction head in each case for the given cavitation parameter value. Now the maximum draft head HS max. The equation we have derived in our previous class. So HS max, you can refer the class note. So HS max equal to PA by W minus PV by W minus sigma C into H. So here we have given EA by W as equal to 9.9 meter absolute. Then PV by W, vapor pressure head is also given as vapor pressure head is given as 0.3 meter. Then cavitation parameter is given. Cavitation parameter, Thomas cavitation parameter, sigma C. Thomas vertical cavitation parameter sigma C equal to 0.36 for Francis turbine and equal to 0.73 for Kaplan turbine. These two values are given. So we have to find the HS max in each case. So for Francis turbine, HS max equal to PA by W is 9.9 minus suction for the vapor pressure head is 0.3 minus 0.36 into H value, head of the turbine is 15. So we get this as 4.2 meter. So this HS actually means height of the turbine inlet abort. So you can install the turbine. The HS max is equal to 4.2 meter means you can install the turbine up to a height of 4.2 meter above the tailpiece. So this is the maximum height of the turbine at which you can install height above the tailpiece where you can install the turbine. Now for Kaplan turbine, HS max equal to 9.9 minus 0.3 minus is 0.73 into 15. So after calculating, you get this as minus 1.35. So you get HS max as equal to a negative quantity for a plant turbine, and the negative sign actually indicates that the plant turbine is needed to be installed below the tail race level, and the depth should not be less than 1.35 meter. So the plant turbine is required to be installed below the tail race level by a depth not less than 1.35 meter. That is why the negative sign comes to it. It has to be installed below the tail race. So that we come to the end of the problem, and also the end of the tutorial 8. Okay. So we'll meet again with another tutorial. Okay, in the next class. Thank you very much.